Okay, the last thing that we need to talk about in 4.3 is rotational symmetry. So a figure has rotational symmetry if you can rotate the object 180 degrees or less about the center of the figure, and then it's mapped onto itself. Or another way to say that is if a figure is mapped onto itself, you basically end up with the same figure. So again, a figure has rotational symmetry. If you can rotate the figure 180 degrees or less about its center. Otherwise, if the requirement 180 degrees or less wasn't there, then everything would have rotational symmetry because you could rotate something 360 degrees and you'd have the exact same figure. Okay, so it has to be 180 degrees or less about its center. And then the center there would be the center of symmetry. So, for example, okay, I could take a square. This square has rotational symmetry. You could rotate this square 90 degrees and 180 degrees. So think about it like this. If I took this point, let me label this, square ABCD. If I rotated this square 90 degrees, again, if it's 90 degrees, that would imply 90 degrees counterclockwise. Then point B would rotate to point A would rotate to point D, D to C, etc. Okay, so this has rotational symmetry, and then specifically the angle of rotation would be 90 degrees and also 180 degrees. If I rotated this square 180 degrees, then point B would be where D is. So this would be B prime, D would be where B is, this would be D prime, and so on. So this has rotational symmetry, specifically of 90 degrees and 180 degrees. Not 270, has to be 180 degrees or less. Not 360, again, 180 degrees or less. So think about other figures that could possibly have rotational symmetry. So I want to determine whether these figures have rotational symmetry, and then if so, besides yes or no, it has rotational symmetry or it doesn't, describe any rotations that map the figure onto itself. So what that means is figure out the angle. What I actually have here is what's called a regular pentagon. If a polygon's regular, all the sides are congruent, like the tick marks given here, and all the angles are congruent. So this pentagon is what's called a regular pentagon. Think about it, maybe pause the video. This regular pentagon does have rotational symmetry. But think about the angle of rotation as well. So for the angle of rotation, here's what you can do. I'm going to label each of the vertices, A, B, C, D, and E. The center of rotation would have to be the center of the figure here. And to figure out an angle of rotation or the angles of rotation, because it's possible, like on the last example, that we could have more than one angle of rotation. I'm just drawing rays from the center through each of the vertices. All these angles, maybe I should use 2 tick marks, are congruent with each other. And then to figure out the angle of rotation, so if I go from ray, just call the center OB, all the way back to OB, that's 360 degrees. I just divided that up into 5 congruent parts. So if you take 360, divide by 5, this angle right here is 72 degrees. Again, that comes from 360 divided by 5. So rotational symmetry of an angle of 72 degrees. So if I rotated this pentagon 72 degrees, B prime would be where A is, A prime would be where E is, and so on. But that's not the only angle of rotation, because I could rotate 72 degrees, not just once, but twice. In other words, 144 degrees. Okay, that's less than 180. If I took 72 degrees 3 times, that wouldn't work because that's more than 180 degrees. So only 2 angles of rotation, because for something to have rotational symmetry, it has to be 180 degrees or less. And then on number 11, okay, just have that quadrilateral. That's all that it is. It's not a square, it's not a rectangle. It's not a trapezoid or anything else. It's just a quadrilateral. Think about it. Maybe pause the video for a second. See if that figure has rotational symmetry. When in fact it does not. So no rotational symmetry, which means there's no angle of rotation for number 11.